Okay, so I think I'm audible now. Okay, so before starting that, let us revisit what we have discussed previous class. So we were discussing recursion and backtracking. So the main idea was that suppose we have a bigger subproblem P, and we were kind of dividing it into, since this is a very big subproblem, we're kind of dividing it into smaller subproblems, namely P1, P2, P3. Again, divided it into some smaller A1, A2, A3, and kind of till we get our smallest subproblem that is easier to solve or we know its answer. That is my base case, right? So once we have divided into these subproblems, then I hope that, yeah, we have found this answer. Okay. So we were kind of recursing way down the tree, recurse, then till we found this answer, we'll kind of backtrack, again we would recurse, and then backtrack, again recurse, then backtrack, right? So this was the main idea of recursion backtracking. And four important points related to that was, first thing, that we need to identify our biggest subproblem, that is in this case is our P, and then divide it into smaller subproblems, okay, such as P1, P2, and P3. And how can we evaluate these P1, P2, P3 to get the answer of these P, right? Another thing, we need to identify our smallest subproblem, that is in this case is AI, that is our base case. And lastly, return our biggest subproblem, that is return the answer of P, return the answer, right? For example, like we have an array, we're kind of divided into, we need to find its sum, let the elements be 1, 2, 3, 4. So we'll divide it into this 1, 2, then 3, 4. Again, we divide this into 1 and 2. And these are my some base cases, because sum of array of one element is basically the element itself. So I was returning 3 here. Then here 3 plus 4 is 7. And all together we return here 3 plus 7 equal to 10. So it was kind of very easier. Okay. So we were some figure some problem, and we are kind of dividing into smaller subproblems. But when does this concept of dynamic programming come? Like, it was all right, no? But if I reframe the problem, let me reframe the problem. Again, I am dividing the biggest subproblem P into three subproblems P1, P2, P3. Okay. Now, what I would do, I would like what I found is that suppose this is divided into smaller subproblems A1, A2, A3, right? And this P2 is also divided into some repetitive subproblems A2 and A5, and this P3 is somewhat divided into A1, A6, A7. One thing to observe here is this some subproblems are being repeated in multiple subproblems. Okay, some smaller subproblems are being repeated, where in this case is A1 and A2. So A2 is also being repeated here and here. So if we like simply do recursion, it will hamper our efficiency of algorithm, because we are recalculating things. Okay, so once we found the answer of these, so these are further divided into smaller subproblems. And once I found the answer of A1, Still, I have to go down the tree and find this answer. But I have already computed my result here. So something I need some memory. Uh, wait, and yeah. So I need some memory to store the answer of certain sub-problems that are repeated, that are, I think, famously called as overlapping sub-problems, right? Because if I have found this answer, I have computed the result of this sub-problem, I do not need to again recompute it. I need some memory. I can store the result like some subproblem S and its value here. So the value of A1 here, and write value of A2, and then I write B2, B1. So it's kind of memory structure I need. So this technique is called as memoization, memoization, and this whole concept of optimizing my recursive algorithm is called my DP, that is dynamic programming. So I can write it as, in simple word, is recursion plus memory. This is my whole concept of DP. Okay, so if you look at the PPT, you can hear like, okay, so we're breaking a problem to smaller subproblems, getting answer for a bigger subproblem from smaller, and getting our bigger base case, and what is our biggest subproblem. Again, since subproblems are being repeated, so I can like compute it once and store it results somewhere, and then reuse this stored answer whenever I need it. So DP is that optimization technique that stores the results of some already solved subproblems. Okay, let us start with some problem. So there's a famous problem known as Fibonacci series. So the problem is finding the nth Fibonacci number, right? So let's start with the brute force recursive algorithm. Suppose I need to find f6. So if you don't know Fibonacci number is that, my first Fibonacci number is 1, and second number is also 1. And for n greater than 2, Fibonacci number is, this is 1. For n greater than 2, Fn is equal to the sum of previous two terms, that is Fn minus 1 plus Fn minus 2. Okay, so if I want to compute F6, I can like divide into two parts, F4 and F5. Okay, to get the answer of F4, I can like divide it into further subproblems, F2, F3. For this F4, F5 again, you can see I have some overlapping thing. F3, it should be F3, yeah, F3, F4, till I get my base case. That is, again, here F2 is my base case. So my smallest subproblem, which is trivial to solve, and this is F1, F2, and kind of. You can see certain subproblems here are being repeated, like F3 here is here, F3. My F4 is also here. F4 is present two times. I'm computing F4 here, and I'm getting F4 also here. Okay. So if I made some data structure which stores my results of subproblems, I can like enhance my algorithm to compute the Fibonacci number. Okay. So this data structure is nothing. I will call it DP. So it is 1D DP. Okay. So its index, if I like maintain what it denotes, 1, 2, 3, 4, 5, 6. So ith index denotes the value of ith Fibonacci number. Ith Fibonacci number. Okay. So in this way, if I have, so when I would like backtrack from here, and then I will again recurse here, then here. So I will check whether this subproblem is already computed or not. And if it is computed, so I will simply retrieve the value from this array, DP array, and get my answer. So I don't have to traverse down the tree, right? And if I have computed this F4 here, I can store this, the result of F4 here, and I don't need to recurse down the tree. Okay. Okay. So there are some terminologies that are related to DP. Okay. So first thing, whatever we have discussed here, okay, some subproblem, bigger subproblem, then smaller subproblem. So here each subproblem, here if I say here my Fi is representing my ith Fibonacci number, since ith Fibonacci number. So here each subproblem is called a particular state, that is DP state. So I can write DP of I as Fi, that is ith Fibonacci number. So DPI is my particular state. Now, what was the second thing we discussed? Okay, how can we divide into P1, P2, P3, and how these subproblems can be used to compute my P, that is the bigger subproblem. So I need some relation which is given here, like, yeah, this relation Fn equal to Fn minus 1 plus Fn minus 2. So I can write is dP of I, my bigger subproblem, can be computed by dP of I minus 1 and dP of I minus 2 and plus addition sum of these two states. So I need some relation here to compute my particular DP state, and this relation is called as transition. Okay, this relation is called transition of DP states. Okay, again here third thing is that my smallest subproblem, that is the base cases, it is same as that we have discussed before. So dP of 1 is 1 and dP of the second Fibonacci number is also equal to 1. Right. Now, fourth thing is, what is my goal? What is my goal? That is, what is the biggest problem I need to solve? Okay, so in this case, since I need to find the nth Fibonacci number, so my goal was basically finding dP of n. Right, it's my goal. So four things: one state which represents each subproblem, and also to like getting the answer of a particular state, I need some relation from its smaller states, that is called transition. Another, the simple base cases, my smaller subproblems, and my ultimate goal. Okay, these points are like discussed here. And basically, if I talk about application in the coming classes, when we will discuss the graphing algorithm for finding distance between two nodes, smallest distance, we need some memorization techniques. Okay, so we can store some, there are some overlapping subproblems there, and I need some DP states to store those answer of those problems. So in those cases, we can use DP and number of ways. Okay, number of ways to construct arrays. Okay, so we can think of a particular state, and using that state, we can compute our answer. Also, whether a path exists or not, we can easily find out using this dynamic programming concept. Okay. Now, if we look at the codes of DP, the Fibonacci number, okay, so this was my initial brute force recursive approach. So I was computing Fn, and Fn is nothing but return the value of Fn minus 1, and these are my best cases. So here the time complexity is basically 2 to the power n exponential time complexity, because in each case I have divided into two subproblems, Fn minus 1, Fn minus 2. Again, this is divided into Fn minus 2, Fn minus 3. I'm not at all storing the results, Fn minus 4 and Fn minus 3, like that. Okay. 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 So using DP, let's see how we can optimize this. So there are two ways to write a DP code. One is iterative DP and other is recursive DP. Okay. We will discuss in details and also jot down the differences. What are the general differences between them? Okay. So first of all, uh, here I'm storing that whether a subproblem has been computed or not. So I need some check. Uh, I need some check. This check will tell me whether a particular subproblem Fi has computed or not. Okay. If it has not been computed, we need to compute. Else else we can retrieve or update its value. Right. Okay. So here in this case, since each Fibonacci number, whatever I store here, each Fibonacci number has a positive value. This will be 2, then 1 plus 2, 3, then 5. So each Fibonacci number is basically a positive integer. So in order to check whether a subproblem is solved or not, we can initialize my whole DPS something called -1. Okay. This -1 acts as a check whether a particular thing, whether my f of 3 is calculated or not. F of 5 has been computed or not. Okay. So that's why when I see the code, okay. So yeah, we're having a certain global DP array. Okay. That will store the answer of my subproblems. And okay. So I'm basically calling the F function. What it does, these are my base cases. Okay, base cases. And yeah, this is a check. If dp of n is not equal to -1, that is, this subproblem has already been solved, just return the value, whatever I have stored here. Okay, just return the value. Else calculate fn minus 1, my n minus 1th Fibonacci number, calculate n minus 2, my n minus 2th Fibonacci number, and store this result in dpn and return the result. Okay. In this way, we have like not already calling fn minus 1, fn minus 2 in all the cases, but having a check function. Okay. So here, what we are doing, like whatever I have fn, we are going to fn minus 1, simple recursive. So we are going from top to bottom. This is my top and bottom. So recursive DP is also called top to bottom DP, or this is called my memoization technique. This technique of recursive DP is called memoization, top to bottom approach. Okay. Another thing we can solve this problem is by iterative DP. So what it does is, okay, So it doesn't do recursive calls all the time. Since each, if I like maintain the array, what is my DP array? Yeah, right here. So here you will see that a DP at particular position I is basically the sum of I minus 1 and I minus 2. Okay. So we can simply iterate our way. We can simply iterate every state from this relation. This is my transition. These are my base cases. Okay. And ultimately, this is my goal. That is my biggest sub problem. And this is my transition. So here we are not doing recursive calls, and we are kind of not wasting our stack memory, because every recursive call uses some kind of stack memory, and it kind of slows our running algorithm. Okay. So in this way, we are saving our space and time complexity. Okay. We'll discuss the space and time complexity in a few moments of dynamic programming codes. Okay. So here, if I write it, we are going from the smaller base cases, and we are calculating F3 here. So from F2 and F3, we are going to F4. From F3, F4, we are calculating F5. That is my DP5. So we are kind of going from bottom to top. So this is called bottom to top DP, bottom to top DP approach. And this technique is called tabulation technique. Okay, since we are, this name suggests we are storing the results in sub table. Okay, so we are storing it here, here, here. Okay, smaller sub problems, and then from these sub problems which has been computed, we are finding these answers. Right. Okay. Now let us discuss what are the differences of iterative and recursive DP. So yeah, my yeah. So yeah, as I've already told, recursive DP, that is my memorization technique, is kind of using function calls and requires a recursion stack. But I can implement my iterative DP or tabulation bottom-up approach. So it uses only loops and no such stack memory is used. And that's why it has a faster execution. But here we need to determine the flow. Since if I talk about the flow, here we are going from I equal to 3, then n. In some cases, when you will solve some problems, maybe you require to go backwards from n minus 1 to 1. So in this way, you have to determine the correct order. Right? Correct order of computation is crucial. Here, flow and order is not so much important, because we are doing simply, we are from the biggest sub problem, we are kind of uh, calling the recursive things. And if it has been computed, we're returning the answer. So we're not uh, getting any order or something. We need our result. So in the, I can say it's like it is a optimized brute force approach, because I'm not applying any greedy algorithm here. I'm just computing all results and storing it somewhere. So that's why you will also find this is famously called as optimized brute force approach. Okay, if we have discussed these, okay. Okay, time and space complexity. Okay, so if I talk about the time and space complexities here, simply you will say that first space complexity. Okay, so here you will see that I am already storing an auxiliary DP array and nothing much. Okay, here global DP array and here also global DP array. So this alone is using my space. So I can say is that space complexity is nothing but my number of states, okay, that the DP array has. Okay, so in this case, Fibonacci number, the space complexity is O of number of states, and that is O of n. Right? Okay. Next, if I talk about this time complexity, since okay, so time complexity is calculated as number of states and into my transition cost. Okay, okay. So since I am computing each state and each state I am calculating through a particular transition relation, that's why the formula is calculated as number of states and transition cost. Okay. In this case, the transition cost, I'm simply doing dp of I equal to dp of I minus 1 plus dp of I minus 2. So addition can be performed in O of 1 order of time, constant order of time. So my time complexity is basically number of states, that is n, into O of 1, right? And it would be O of n, as simple as that. Okay, so basically if I like visualize it in a graph, so these are some sub problems, 1, 2, 3, dot 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 I, and these are my transition costs. So each has a particular constant transition cost, that is C. Okay, so I'm like simply the time complexity would be area under this curve. Okay, I hope you're able to understand why this formula is written here. Okay, uh, right now next. Okay, what if this is my case one? What if my different states have a different transition cost? Suppose my DPI state has a transition cost of something like n by I. Okay, so here, so the transition cost, this is my transition cost and over state uh, coordinate system. So D of 1 has a transition cost of n, 2 has a transition cost of n by 2. So every one has a different transition cost, and in this case my total time complexity would be simply the area under this curve, which is not at all can be found using a any formula. So basically we are like summing all the individual transition cost here. Okay, so we can write it as summation of all transition cost I, Ti, from I equal to 1 to n. So in this case, it would be like n by 1 plus n by 2 plus n by 3 and dot 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 n. So if I like take n common, it would be 1 plus 1 by 2 plus 1 by 3 dot 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 1 by n, right? And this is simply a harmonic series and its value is something log of n. So it would be n log of n, my total time complexity. Okay, but but my space complexity remains same. That is order of number of states. That is O of n. So there are two cases to finding the time complexity. You need to determine whether your state transition cost depends upon I or not. If it is not, you can simply like apply this formula. Else you can apply this formula. Okay, this is a universal formula. Okay. Now let us solve a particular problem which will summarize all the concepts that we have discussed till now. Okay, so yeah, like here all the points are mentioned. Yeah, if it has n by I transitions, total work done is n log n. Okay, transition performed by each state, summation of Ti. Right now, okay, let us read the problem. Okay, so here these are houses. A professional robber is planning to rob houses along the street. Each house has a certain amount of money. So house one has one money, 2 rupees, 3 rupees, and 1 rupees. And the robber cannot rob adjacent houses at a time. And we need to determine what is the maximum amount of money that robber can rob. Okay. So it is the problem. Okay. So I have a certain array. Let me decrease the size. And yeah. Okay. So I have a certain array 1, 2, 3, 1, which represents the money that each house has. One, house two, house three, house four. And the robber cannot rob adjacent houses. Like if he has robbed this house, he cannot rob this house and this house. Okay. And so total money he can got is 3. Else he can do is like rob this house, skip this, and again rob this house, this, and skip this. So in this case, I'm getting my answer as 3 plus 1, that is 4. And my answer is basically 4. Rob house 1 and 3. Okay. So if I identify my sub problem is basically what is if I like define my state as what is the maximum amount of money I can get from first I houses. Okay, I am like defining my state as this maximum amount of money I can get from first I houses. Okay, what will be my base cases? Okay, so dp of 1 would be simply the value of a array of 1. Okay, from only one house I can like rob that house. Okay, I'll get my value as a of 1. What will be dp of 2? Okay, so I have two houses with value 3 and 4. Okay, it will be max of a1 comma a2 because I can rob only one out of them, and I will rob that house that have the bigger amount of money. Okay, larger amount of money. And now we have to define our transition in order to compute our larger subproblems. So I can write it as dpi is equal to, suppose these are my houses, 1, 2, 3, dot 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 I minus 1, I minus 2, I minus 1 I. So if I rob this house, I should not have been robbed this house. So I have to determine what could I have robbed, what could I have got from these I minus 2 houses. So I have two choices. One is take rob from this house, rob from I, and not rob from I. Okay. So if I'm robbing from outside, so my answer would simply A of I plus the maximum amount of money I could have got from I minus first I minus 2 houses, or else I chose not to rob from I. So I can simply like include this I minus 1 house, and I would simply write what could have been my answer from first I minus out houses. So my required transition is dp of I is basically max of ai plus dp I minus 2, comma dp of I minus 1. Right. This is my required transition. So this was my state transition. My base cases are also done. And now what was my goal? My goal is what was the maximum amount of money I can get from first n houses. So this is my goal, dp of n. Okay. Let's look at the code. Yeah. So yeah, if n equal to 1, return the first house only. Okay. dp of I represents maximum amount of money I can rob from first I houses. These are my base cases. And I have two options, to rob or not rob, and computing this transition and ultimately returning the final sub problem here. Okay. Another thing is that uh, space optimization we can do in DP. So here you will notice that whatever I am calculating is DPI, I am only considering the previous two states. If you clearly observe, we are only uh, associated with the previous two states. So if this is I minus 2 and I minus 1, my I depends upon this previous two states. So instead of storing all these in an array, what we can do, we can simply like take two pointers, previous one and previous two, and from this we can calculate our current result. Okay, we can simply just take previous one and previous two pointers. Okay, and then compute our current answer and then updating these pointers. So in this way we can like calculate all in order of one time complexity, space complexity. Okay, let's look at the code. Yeah, so we are like taking two pointers, previous two and previous one, and traversing an array, and only like basically associating with previous two and previous one pointers, and then finding out answer. So in this case, in that case, our space complexity of O of n, and in this case, our space complexity is of order of 1. So in this way, we have like find our answer. I hope this is all clear to you. Now handing over to Sarthak from discussing the rest questions. Okay.
Okay, I hope I'm audible and my screen is visible. Okay, so let's practice some question to further learn the concept of dynamic programming and how it's useful in solving the questions easier than the previous approaches. Okay, so the next question is removing digits. So in this question, what you need to do is you need to select any of the digit in the number given, and then you can subtract it. And the end goal is to make the number zero. So what basically you gotta do is that suppose if our number is 29, then we have an option. We can either select 2 or we can select 9 and subtract it from this number. Suppose I selected 9, then the number becomes 20. Then I again have an then I don't have any option really, because you can either subtract 0 or 2. So I subtract 2, it becomes 18. Then I have an option to subtract 8 or 1. So I will subtract 8, it becomes 10. I subtract 1, it becomes 9. And after that, subtract 9, it becomes 0. So basically, this took me 6 steps. So the thing is that this question can't be solved greedily. Like you might be thinking that the bigger the number that you select, the better it's going to be. Like if it's 20, if I have an option like 87, then I select 8, then I reach the answer earlier. But it doesn't always work like that. Okay, so it might be possible that subtracting 7 will get you 0 earlier than subtracting 8. So you can't really say that what subtracting what, like it's not necessary. Like it might happen that among 97 and 67, it is possible that 97 will become 0 faster than 67. Like 67 will require more steps. So how do we approach this? Like we need to like let's suppose the constraints are 1 in 5. So we need to get it done in like n log n, or n under root n sort of thing, or just n. So how do we do this? So the thing is that uh, if it's not working greedily, then we need to try out all the possible cases, right? Like suppose if the number is 18, then I'll also need, then once I'll subtract 8 and check for 10. In the other case, I can subtract 8, I can subtract 1 and make it 17, right? When it's 17, I still have two options. I can either make it 16 or I can make it 10. And so I made it 16 once, I made it 10 once. Then in 16, again, I have two options, right? So this like recursion is the way to move ahead, right? Like we can just recursively see that what's the suitable answer. Like we can consider all the cases. But the thing to note here is that all the numbers will have two possible scenarios, right? So, as we have learned in the earlier classes, the recursion tree and the recursion time complexity is going to be very, very, very extensive. So obviously, like even if like as I mentioned, the time complexity is somewhere around 1e5. The constraints are somewhere around 1e5 here. But even if it were like 1,000, it still wouldn't pass because as recursion, it's going to 2 to the power of n, right? So it's no, no. So this is not way forward. So what do we do now? So like obviously we are learning DP. So this is going to be optimized using DP. So the thing is that there are going to be 1e5 cases, right? Like all the numbers that I get are lesser than 1e5. So what I can do is that suppose if my original number is 0, then how many steps is it gonna take? It's going to take 0. If my number is 1, it's still going to take 1 step. If my number is 2, this is going to take 2 step. Like again, it's going to step 1 step. If it's 3, then still 1 step. So basically till 9, it is going to remain same. Then when I'm at 10, so the thing is that if I have like all the possible scenarios, like there are two scenarios, I can either subtract 0, like 10 is not a good example. Like let's go with something like 23, right? So there are two examples. There are two cases. We can either go back to 20 or we can go back to 21. So all the cases are smaller than this number, right? So a neat thing about DP is that if you are able to figure out the state properly, then like half of the thing is already done, right? So whatever be the scenario, you are going to require, if you know like the the lesser values to which the number can be reduced, then if I know that suppose to get 21 I need x steps, like for 21 I need x steps, right? Then for 23 how many steps am I going to need? I'm just going to need x plus 1, right? So basically, if I already know, like I till 9, I know the number of steps is 1. So what is going to be the number of steps for 10? It's only going to be 1 plus 1, right? It's going to be 2. So that is the thing that in any number that I have, if I have already pre-calculated all the smaller numbers up to that number, then I'll like suppose like the complexity is the same, the constraints are till 25. So they're going to be 5 digits at maximum, right? So I can check for all the 5 digits. Like suppose my number is very big, it's something like 98674. 3. Then for all the possible, like I can once check that what happens when I subtract 3, what happens when I subtract 7, what happens when I subtract 6, what happens when I subtract 8, and so on. So if I know all those 5 smaller numbers, like all the like if the number of steps required till the smaller number when I subtract any one of the digits is x, I just need to add plus 1 and I'll get whatever be the least steps up to this number. Okay, so now I think the implementation gets very simple, and the time complexity is n into whatever, like it's 5. So it would be somewhere around n into 3 types, but like n log n would be the formal definition of that. So then I hope there are no doubts in this. So it's pretty easy to implement this. Like we know you can just for like so this what will the state of the DP. So the state of the DP would be DP of X would imply like something like the least step to get X. Okay, so this would be the state of DP as I mentioned. Then you can define the base case. So base case is DP of 0 is equal to 0, right? So this would be the base case. And after that, it's simple. You just keep for like for whatever I till n, you'll just iterate and you'll just keep checking, right? That like you whatever be the digits, suppose like let's call the digit D, then whatever is the digit currently we have, we'll just check, right? That like for whatever be the DP of X, that would be we need to calculate the minimum steps, right? So that would be DP of x and minimum of dp of uh, x minus d being the digit, right? So if you just go through like this till n, so your answer is going to be dp of n. I hope I'm clear with the pseudocode. And so like we can formally check this out. So the solution is, as I mentioned, okay. So as I mentioned, it's an log of n, and we define the base case as dp of 0 is equal to 0. And then for every particular digit, we just check. Okay, like one thing that I missed out here was like we'll also add one, right, for the current step that you are performing. So for every digit, you'll just, if the digit is 0, then it's no use of subtracting it. So for every other digit, you're just going to check dp of I minus digit. And for all the digits that are present in the current number, you will find the steps. And finally, dp of n is going to be your answer. I hope I'm clear with the explanation. Now, let's move to the, okay, so this 0 1 knapsack is a very standard problem. Okay, let's see db this 0 1 knapsack after solving this edit distance. Okay, let's move basic. So okay, so what we need to do in edit distance is we are given two strings, right? Word one and word two. And we need to return the minimum number of operations that are required to convert word one to word two. So like, and what are the operations? There are three permittable operations that we have. We can either insert a character, delete a character, or replace a character. So as the examples here state that, okay, okay, so as the example here states that if we are given horse and we need to convert it into rows, then we can just replace an H with an R. If we need to convert rows into rows, we can just remove R, and simply rows into ROS would need you to remove E. So we need to minimize the number of steps. Okay. Uh, so the question would be to the minimum number of operations that you have to perform. Like the thing is that suppose my first number is, okay, horse. Suppose it's king and second is ki. So I can just remove n and g and it becomes ki, right? Or so the thing is I need to give the minimum number of operations that I can perform. Okay. So in this the thing is that it's not always optimal. Like there is no greedy approach that you can perform, right? That removing from end, replacing operation or anything. Like there's no such approach, right? That like would give you a straight direct answer. Basically, you would have to consider all the given possibilities. Like in this, okay, let me see for a good example here. So so the thing is that if the words are king and kin, then you can also like you can remove all the letters from this and you can remove all the letters from this. So all so both the words becomes empty strings, right? So then even then your answer matches, but it's not optimal. So how do you like get the optimal approach for this? So in this case also the thing is that you can consider all the possibilities, right? That suppose if my word is Tom, then I can consider the all the possibilities using recursion, right? Once I can remove T, once I can remove O, then I can remove M, and then I can remove T and M, I can remove O and M. So then again it becomes a very big time complexity, which is not nice. So how do we optimize it? Like I need to convert Tom into O. So what do I do? So the thing is that in this, generally, like what you can do, you can just remove all of them and then add an O. So that would take you 4 steps. But that is not ideal because you can just remove T and M and you can stay with O. and so that would take you 2 steps. So now, how do we find, like, how do we do this? So then again, like in this, I would be telling you the DP states beforehand. Now, obviously, it's not very intuitive uh, in the first attempt, but once, like, it is a very general approach in solving DP questions, like one of the very famous approaches. So, as we already stated, that first you need to find the state, right? So you can just guess the state and see if it works out. If it doesn't, you can try something else. But in these sort of questions, it's very easy to see the state. So the state of the DP can be DP of I and J. So what would my state DPIJ mean? So what DPIJ basically means that I am in the ith index of the first word of the first string and jth index of the second string. Okay. So, and what would it mean? That if I'm in the ith index of first string and jth index of second strings, and after like reaching to where I am, what is the minimum number of operations, right, that I have required till now? Like till now, I don't care what will happen after this, but till now, like also a major thing in DP or recursion problems is a leap of faith, right? That you need to trust that you have already calculated things, and you need to make some jumps. Like you don't need to exactly visualize while solving the problems, right? Like you need to, at certain moments, you need to make a jump without like exactly figuring out all the things, but you know that somewhere you might have calculated this answer before. So if I am at ith and jth, like suppose my word is not Tom, it's something like this, and my second word is this, right? So in this, the thing is that you need, if I'm at if I'm at h here and I'm at j here, okay, then up until this position, what is the least number of operations I have performed to make both of the strings identical? Okay. So in this, there were three operations we given to us, right? Replace, add, or remove. So the thing is that if suppose I'm not at J and I'm at H. So if the H in both the strings are equal, then do I need to perform either of the three operations? So no, right? Like if it's already same, I don't need to perform any operations. So now let's talk about the transitions. Okay. So this is the easiest transition to see, right? That if like whatever S is the first string and let's call Q the second string, right? If Q of I and Q of J are equal, then I don't need to perform anything. Like all the three operations, since I need to minimize, I won't be performing any operations. So what would I do? So I don't need to add any number of operations. So basically DP of I and J is just going to be whatever be the last index of this one and last index of this one. Since I'm moving from left to right, I've already calculated for I minus 1 and J minus 1, right? So whatever would have been the minimum for that, I would just let it remain like that because I don't need to perform any additional operations right now. Okay. But what happens when it's not like that? When the numbers are not equal? Like suppose, as I mentioned, we are talking about. Okay, so if I'm at J here and I'm at H here, well, then you have various like three of the options, right? You can either remove J, you can remove J, right? Or you can add something here, or you can replace both of J and H. Like, or you can replace J. Okay. You can either remove it, replace it, or add something to it. So let's try to figure out the transition for all of the three things, right? Let's say I removed let's say I removed J. What would happen then? If I remove J, then whatever, like if I was at ith index now, then I would be at I minus 1 index, right? And in the jth case, I and in the second string, I would still be at J, right? And since I performed an operation, it would be plus 1. So am I clear with this? Because since you are removing an element, so if I removed j, so I would check that before this j, whatever the element, since I need to make both the strings equal, so whatever might be the element before this, that should have been equal to h, right? Like this is t, but whatever, like when we had calculated for these strings earlier, then we would have calculated the number of operations to convert t into h, right? So we would just take a leap of faith here, and I minus 1 j plus 1. This is for this is for deleting, right? Now the second would be to replace. Like if what happens if I replace, then if I replace j, then I would just replace j to be h, right? And they would both become equal. So then I would again go to dp of I minus 1 j minus 1, right? And since I performed an operation, it's plus 1. If this would be for replace. And what would be the third condition? Third condition would be to add something. So what do I add in this number? So if I add something in this number, I would just like if I need to add something after j, then I would surely add like okay, then I would surely add h, right? So that it becomes equal to the last, like O by H. H is our last in this string. So I need to add something in this string. So if so I definitely add something so that the last becomes equal. So I would add H in this string, right? So if I add H here, so basically the number which I was considering was J. So so this should become equal to the previous one. Like OY should be equal to whatever up till J. So basically what happens is I this time I would go behind in dp of j minus 1, right? So I would remain like that, and this would become j minus 1, and since performing plus 1. Now, among these three, I would take the one which gives me the minimum, as we need to calculate the minimum steps. So this would be the transition if the numbers, if both the characters are equal, and this would be the transition if they are not equal. And accordingly we would consider the minimum, like out of these three we would take the minimum, and finally our answer would be dp of okay, so finally our answer is going to be dp if the length of string 1 is n and the length of string m is m, so q is m, so this is going to be our answer. And so I hope I'm clear with the question. Now, another thing can be defining the base case, but the base case in this is pretty simple, right? So, suppose if I am at uh, my first index is kin, my first string is kin, second string is hu whatever, and if I am at the starting 0th index of the second string, then what do I need to, how many operations I need to change this to the second string? Like kin to empty string. So basically it's 3, right? If it was kin G, then the answer would be 4. If it was Y, then the answer would be 5. Similarly, if I am at HUH and I need to convert this, and I need to convert an empty string to HUH, then again I would require 3 additions. So basically it would just be the size of the element. So that would just be like at if I am at dp of I and 0, then this would be I, right? If I'm at dp of 0 and j, then it would just be j. So these would be our base cases. I hope I'm clear with that. Let's see the solution. So, and yeah, the time complexity is n into m since we're iterating both the strings together. Uh, as I mentioned, the base cases here is defined in the similar fashion. dp of I0 is equal to I, dp of 0j is equal to j. And then we would just iterate in the string. If the characters are equal, then no operation is needed, just dp of I minus 1, j minus 1. Else, there are 3 operations that we can perform. So these are the 3 operations. And since 1 would be added in all 3, so 1 plus whatever be the minimum of the 3. And then we would just output dp of n m. That would be our answer. So this was the second question. And Okay, so now, as there are no doubts in this one, let's move to the third problem. Okay, so this is a 0 1 knapsack problem. Okay, so in this problem, what basically we need to do is uh, that there is a weight specified, right? It's 4 here, and we have some let's, like, I'm not exactly reading it out from the question, but whatever the gist of the question is, that suppose the total weight is 4 and the weight we are given are 4, 5 and 1. So the thing is that we need to select all the weights, and the sum should be lesser than the this weight 4 given here, and every weight has a value assigned with them, and we need to maximize the value. Like suppose it's 4, then I can either select 4, so the value would be 1. Another possibility is I can select 1 and the value would be 3. Another possibility, okay, so there are no more possibilities because we can't take 5 as it is greater than 4. So 3 is our best possible case. Now again, you can't go with greedy here because there's no fixed proportion here, right? It might be possible that the lowest weight, like the, okay, it might be possible that the lowest weight has the highest profit, right? And it also might be possible that the lowest weight has the lowest profit. So it all depends on the current question, the current case we have. So since there is no set pattern here, you can't apply greedy. So the thing is, you have to take into consideration all the weights that you can take and you can't take. Like you can try leaving it out and basically see what is the maximum value that you can achieve. So again, like taking and not taking, that it reminds us of recursion. And for every index, if we are trying to take and not take, that's 2 to the power n. But that would be very, very slow. So we are going to optimize it using DP. So we can break it into smaller sub problems and try to figure out how to solve them. So I hope I am clear till this point. And now, like, let's think of what our case can be. Like, since we are breaking it into smaller sub problems, suppose, like, it can be defined either way. Like, it can be, okay, so n would be the size of the array, and w would be the limit on the weight. Okay, so let's just say that we this is our state. This is our state. So what would our state, like, what how can we define our state? That whenever we are at a particular index n, like whenever we are particular, suppose our index is something like the value is 3, 5, 4, 5, and the weights are something like 4, 3, 4, 3. Okay, so whenever I am at a particular index 4, suppose I am at index, like, I'll be speaking in one index form since it's easier to understand. Suppose I'm at the third index and I'm cons- I'm at the nth index. Okay, let's just I'm at the ith index, which is 3, and the weight I'm currently considering is, let's say the weight I'm currently considering is 3. Then what is the maximum value I can produce till that? Like if I'm at the third index and I need the total weight to be 3, then what is the maximum profit that I can achieve with this specification? So now it's pretty clear to see that in whatever happens, whenever we are going ahead with this, like suppose I am considering second index now, But when I would be considering the fourth index, I would require the answer of third index, right? Because if whatever be the maximum profit till this index, and whatever be the maximum weight of whatever weight I am considering, that would also help me in finding the weight when I'm at this index. Like I can either take a particular stone or I can't take that stone, right? But like let's not call it stone, like I can let's call it gold, okay, since there's a value attached with it. So I can either take the gold or I can't take that gold. There might be the thing like there might be a thing like suppose uh there is a gold whose weight is 5, but whose profit is like 1. So I'm more better off not taking this gold, right? If like you can take this gold if you don't have any better options, but if I do have better options, like if I have a gold of 3 whose weight is 1, and I also have a gold of 2 whose weight is 1, so I would rather take both of these than taking this, right? Or it also might be possible that the weight of this 5 is 4, or 5 or 4, okay, so I would take 5 in this case. So that's the thing, you need to consider all of the cases. So our state looks good enough. I could have also done it in the reverse manner, like at one particular weight, I could have indexed through all of the value array. So either way, only that there's going to be just a slight difference in the transitions. But in this case, we are going with TP of NW, right? So now, what are the transitions going to be? Okay, so before the transitions, let's think about the base cases. Okay, so what are the base cases going to be? First of all, we need to like minimize maximize the profit, right? So in the base cases, like when the base case can be something like, suppose, okay, like if I don't have, like suppose if I'm at 0th index, I haven't still started exploring my indexes, and I am at a weight 4. Can this be achieved like without considering any of the indexes? Can I go to weight 4? So this is not possible, right? So I can just fill a garbage value like minus infinity into this, and that wouldn't matter. And after that, what I can do is, so let's move to the transitions. Like we don't specifically need to like we need to assign the base case, but like while explaining that, it would be easier to understand for you guys. So suppose I'm at a particular index I, and I'm at j weight. If I don't mean to take this ith index, right? If I don't want to take this ith index, then uh basically the profit is not going to change, right? And how would it, like what would it be? So this would just be dp of I minus 1 and j. Since I would just like before considering, like if I'm not going to take 4, then before 4, like till 5, what was the maximum profit did I have? So that it's just going to remain same, right? So this is one case. But what if I'm going to take this? Then if I'm going to take this, like suppose currently I'm considering weight 5, right? Like and my current stone weighs 2. My current stone weighs 2. So what do I need? Like, can I make 5 with this 2? Of course I can. But for that, I would already need 3 to be there, right? So 3 plus 2, the weight becomes 4, becomes 5. But what 3 would I choose? The 3 with the maximum profit, right? So I would just check out all the weights 3 and what was the maximum profit I could have achieved till weight 3. And in that weight 3, I would add 2. So basically, what is the transition? It's like very simple, right? I would just subtract the weight from it. So I would just check it out, right? Like before, okay, I would write it down. So if it is dp of like we would go till the previous index, and then like we would just subtract the like whatever the weight was, like we would subtract it. Okay. Uh, okay. So we would just subtract the weight. Like, so what happened? Like currently I was at 2. I figured out what was the maximum weight I could have achieved till 3. And since I'm taking the 2, I would just add the profit in this, right? I would just add the profit of I. Okay, I did my minus 1 in the index because I was considering one based indexing, right? So I would just subtract 1 from here. So basically, these are the two conditions. Like you would have to put a safety net here. The weight can't be less than J. Let's suppose currently your stone weighs 4, and the total and so like the current weight that you're considering is 3. Like the maximum weight you're considering is 3. Your current stone weighs 4. So you can't subtract 4 from 3, right? So you'd have to check that the J's value should be greater than the weight's value of the particular stone. Okay. So that is okay. So these would be the two. This would be the transition. And so let's move on to the code now. So, okay, so this was an example of 2D DP, but like it doesn't necessarily have to be a 2D DP. One thing that you can notice here is that states, like it's just depending on I minus 1, right? Like one dimension is only in depending on the previous one, right? Like J is depending on the weights value. So for J we would need all the weights value with us. So we would need to store all the weights value at every particular stage. But for I, it only depends on the previous I value. So you don't need to carry all of the n indexes with you. You only need to carry one previous index with you. So like that would it would be a bit more clear with the first let's see the 2D implementation, right? So in the 2D implementation, okay, so let me just copy it. Okay, so in the 2D implementation, what we need to do is, so as I told about the state, that maximum value obtaining using only the first I items, okay? And what happened here is that we would start considering from the first index, okay? Because from the 0th index, the profit would always be 0. You have no, if you're not selecting any stones, you won't have any profit, right? So at from the first index we go from weight 0 to weight W, and we'll just check, like if we don't take, then it would just be dp of I minus 1 W. And if we do take it, if it is possible, like as I mentioned it, like here what I explained to you guys through J, W is same as J, so W's value should be greater than weight at that particular index, and then we can take it, and we would just see whatever the maximum, like if not taking, like since see if it was always the case that taking would give us a greater value, then we could have solved this greedily, right? But we only use DP here because we were not sure, like not taking a stone can result into a better answer than taking a stone, right? So among these two we would just calculate, like here is a max function, right? So we just see whatever the max value we can get, and so dp of nw would be the final answer. Now the thing is that as we can see I is depending on I minus 1, so we don't need to carry all of this, so we don't need we don't need this n plus 1 here, right? You just need a 1D vector, right? So to store the weights are very important because you can't predict the j's value, right? J is depending on w minus w weight of I minus 1, so that can be anything, so you need all of the values in your hand at any given moment. But but i's value is only depending on I minus 1, so you only need a 1D vector in your hand while working. You don't need anything else. So for that, what you can do is that at every moment you can just store a vector, like uh, suppose you are having a current vector, right? So in that current vector, you can just transfer all the findings up till that index, and then you can just move ahead, okay? And then you can just keep updating that current vector. So that is what should be done here. Check it out here, right? So what happened is that in this, it's a 1D implementation. Let's go ahead and see. So in what happened in this implementation was that see, as I told you guys that you only need a current vector, right? So in the current vector, you stored like you have these values, whatever be the maximum value at every weight. You just needed all the weights here, and at every iteration you would just update this previous value to current, right? So you'll just keep changing this current, and so only I minus 1 is required in this, and then you can just finally answer previous of w. Okay, so if you understood the 2D, basically if you understood the 2D implementation, converting it into 1D is a cakewalk. It's not that difficult. It's very straightforward. But I showed you guys. So in this case, the space complexity reduces a bit. But like you can use either of the two. Like in most of the cases, it doesn't. It's not much of a bother using a 2D DP because the time complexity is the same in both cases. So that is it. If you have any questions, you may ask me. Uh, and if you don't have any questions, then that's it for the class. Okay. Thank you. We'll be ending the class now.